like to say welcome to everybody, and it's nice to see you back again for another one of our online meetings. I hope everybody's keeping safe and well in these trying times, to say the least. This evening, as I say, we've got Dr. Paul Whiting for this evening's talk. A lot of our long-term regular members will be familiar with Paul. He's visited us a number of times in the past now to give us some of his quite interesting talks. For those who aren't familiar with Paul, he's an outreach astronomer who does a lot of talks to schools, youth groups and whatever. And he's also been traveling the world chasing eclipses and auroras like some of our own members. The talk this evening from Paul is going to be on galaxy collisions, which only recently have been recognised as a phenomenon, as I understand. And I'm sure you'll all enjoy that. As Les says, hopefully afterwards we'll have time to have, I would say, a short, abridged general meeting, somewhat delayed by a few months, but hopefully have some time for that afterwards. So without further ado, thank you very much, and over to you, Paul.
Oh, thanks very much. Let's see if I can share the screen again. It worked the first time. Yeah, seems to be happening.
That's it. It's working.
Right, can everybody see it?
Yes.
Just move the little icons out of the way so I can see what I'm looking at. Right. Well, thank you for inviting me again. I've lost count the number of times I've spoken to you. I must admit, I don't really miss the drive down and up the A12. Although I don't like doing these Zoom meetings, I'd much rather be face to face. It does save that hour and a half drive, but never mind. Right, colliding galaxies. Well, this was an interest of mine when I did the astrophysics degree the other year, the University of Central Lancashire. This was actually my final year dissertation subject, so that's where I got the idea from for doing this particular subject. So, going to kick off, hopefully. Oh, there we go. Hopefully you can all see a bit of moving video there. Now this is a NASA simulation of the Milky Way and Andromeda galaxies colliding. What I'm going to do, I'm just going to let you watch this now, and then I shall play it through at the end of the talk, and hopefully you'll be able to notice one or two things that I shall be pointing out during the talk. It's rather violent. It's obviously readily available if you want to see it again yourselves. Just do a Google search for it. Oh, I'm going to. As our chairman suggested, that galaxies colliding, for what they actually are, a fairly recent phenomena. It was the Toomray brothers who initially had the idea and published the fact that what we've been seeing for best part of 100 years, but they're not new to see, but to actually think what they were and what was causing them, say within the Toomray brothers in as late as 72. Now, it was only in the last 40 years that we've connected these colliding galaxies with different sources of radio frequency radiation. And it's only really in the last 30 years that we've realized the contribution that galaxy collisions makes to the evolution of galaxies and how they progress through their lifetime. Now, as I said before, we've seen images and we've taken pictures of them for the best part of a century. And of course, it was only in the 1920s that Edwin Hubble decided that what we were seeing were not nebula, as they were called before then, but actually discrete galaxies beyond our own Milky Way galaxy. So we've come a long way in 100 and so years, but as I say, in terms of colliding galaxies, it's only really in the last 50 years, I guess. So it's actually quite a rare event because galaxies are far apart, and the interaction when they do start to collide, obviously under the effect of gravity, their interaction speed is extremely slow. But gravity might be the weakest of the forces, but it's certainly the longest lasting. And so once the two galaxies such as ourselves and Andromeda have started coming together, as indeed we are, it is actually inevitable. But there are billions of galaxies out there, and we see lots of examples of galaxy collisions in various stages of interaction, which is good. So although they are rare, there's lots of them because there are billions of galaxies, as it says. And so we see them at the near miss stage or about to meet, during halfway through the collision process, and the resulting devastation. So we are able to study various stages of galaxy collisions because there's simply so many of them out there that we can see. So to start looking at them, we should start thinking about classifying the different types of galaxy collisions. Now, you're probably familiar with the old Hubble tuning fork classification. On the left-hand side, we have the elliptical galaxies, starting with the circular elliptics, getting progressively more cigar-shaped and flattened. And then we get the crossover between the ellipticals and the spirals. And we have the distinction between the ordinary spirals of various levels of tightness of the spiral arms and the barred spirals. And of course, the Milky Way was thought to be a spiral and now thought to be a barred spiral. And anything that didn't fit one of these categories was termed an irregular. So there's ellipticals, spirals, barred spirals, and everything else. And of course, until fairly recently, colliding galaxies were classed as something else, irregular. Something a bit better than that. So Lynn and Forbes in the 2007-2008 came up with the idea of defining the characteristics of a merger based on the amount of gas that's actually contained within one or other or both of the colliding galaxies. So we have two types of galaxy, essentially, roughly. Gas-rich, so they're full of hydrogen, full of gas, lots of new star formations. There's lots of hot blue stars, new stars. So we call those blue galaxies. And we call the older gas-poor galaxies that used up all the hydrogen on star formation. And so all the stars tend to be a lot older and hence richer. And so we call those red galaxies. So we can define wet and dry mergers. So a wet merger is when two gas-rich galaxies, usually spiral galaxies, combine, and you probably end up as an elliptical galaxy, a lot less structure, more compact. And there'll be a lot of star formation triggered during the collision process. There'll be quasar activity triggered most likely, and there'll be a lot of globular cluster formation, which none of those things you get when you get a dry merger between two gas-poor galaxies. And of course, there's the halfway state, there's the damp merger, which is like a wet merger, but less gas-rich. So they're slightly less blue galaxies. And then you get the mixed mergers when you get blue and red types merging, and in which case you it all depends on individual cases, what you get in terms of star formation and quasar activity. An example of a wet merger, they're usually two spiral galaxies interacting. There's numerous examples of these. And of course, this will be what happens when the Milky Way and Andromeda start merging. And here's an example of a dry merger. You can see a lot less sort of spectacular in the visual, but usually two elliptical galaxies. And there's a mixed merger, spiral and an elliptical coming together. So a little bit of statistics here. We tend to, these are the stats at two different distances from us. One at Z is redshift, so that's about 1 billion years ago, or 1 billion, same thing. And the lower set of stats is at a redshift of 1.1, which is about 10 or 11 billion years ago, or light years away. We can see at the moment, close by, billion light years away, we see roughly equal amounts of wet, dry, and mixed mergers. They roughly the same. But as we go back in time, we see a lot more wet mergers, very few dry mergers, and a handful of mixed mergers, about a quarter. So you see very different statistics happening 10 or 11 billion years ago as opposed to a billion years ago. Come back to that later. So another form of classification brought by a guy called Narasimhan in 96, based on the original work by Zwicky in 59. It was based on energy exchanges. So we have this A, B, C, D, CD classification system from small effect, moderate effect, capture without disruption, disruption without capture, and capture and disruption. So it's quite a straightforward classification. So here are some examples. So this is an example of small effect, so it's a type A. And this one is a moderate effect. Now, incidentally, in the middle of this, we have a quasar, 3C278, most probably formed as a result of a merger of these two. And I'm sure you all know, of course, that 3C278 was in fact the very first quasar. So I only spotted that this morning when I was practicing this. I thought, well, I must look up 3C278, and lo and behold, there it was, the first ever quasar identified. We'll talk about quasars later on. Right, so we've seen this one before. This was a mixed merger on the wet and dry scale, but this is a capture without disruption. As we can see, they are now gravitationally bound, but they're still retaining, or the spiral is certainly retaining for now its shape. Might change in the future, but that's what it looks like at the moment. Then we have disruption without capture. So these two have passed through each other and caused havoc on the right-hand side. Then we have capture and disruption. So I can't say it's a very famous one, or I don't recognize it anyway. But there we go. So that's classifying on energy changes. So, collision thermodynamics. Right. Well, the energy involved, as you can imagine, with two galaxies colliding, it's absolutely phenomenal. So if we do a little bit of maths, if we take two galaxies of, say, mass 10 to the 12 solar masses, which is about 2 times 10 to the 42 kilograms, and if they're approaching at about 300 kilometers per second, then simple bit of maths, you can work out the kinetic energy involved is of the order of 10 to the 53 joules. That doesn't mean much. What does it mean? Well, that's the equivalent to the energy produced by about 100 million supernova. But, as I said before, it's very slow progress, a galaxy collision. You can see in the example, they're only moving at 300 kilometers per second, which compared to the size of the galaxies involved is slow. And so it takes about 100 million years, so 10 to the 8 years, to complete a collision. So that energy is dissipated over that time. More sort of manageable thing to quantify and to think about. So a galaxy collision may be defined as, so this is the formal definition, if you like, from Struck. A galaxy collision may be defined as a close encounter of two or more. We quite often see 3 or 4 galaxies colliding, but they're all in the same group and they're all gravitationally bound. So that's not too surprising. Such that there is a gravitational tidal interaction that has a substantial effect on at least one of the interacting bodies. So that's a formal definition which has become sort of the de facto definition of what we mean by a galaxy collision or colliding galaxies. But the term collision is really a misnomer. So if you think about it, given the size and number density of stars within a galaxy, the chances of any 2 stars actually striking each other is something like 1 in a million billion for a star which, like the sun, is, you know, on the outskirts of one of the spiral arms of the galaxy. So 1 in a million billion. Still better chances than me winning the lottery, but there we go. It improves, the probability improves slightly if you're a little bit further in towards the galactic core, but only by a couple of orders of magnitude. So it's still very low probability that any 2 stars will collide in a galaxy collision. So they're not really a collision, they are an interaction. The material that's affected most by these interactions are the various populations of gas sitting between the stars that we call the interstellar media. Sort of interactions will take place? Well, how can we describe this? Well, one of the metrics that they use is to describe the resulting shockwave from 2 clouds of gas colliding. Now, the shockwave will very much, the resulting shockwave will very much depend on the thermal state of the gas. So we define it in terms of the speed of sound, or the Mach number. So we're looking at longitudinal waves. Obviously, we're not talking about sound as sound, but longitudinal waves within the shockwave. And so for cold cloud collisions, so imagine clouds of cold hydrogen, for example, because it's mostly hydrogen we're talking about, typically about 100 degrees above absolute zero, so about -173 centigrade, that's 100 Kelvin. The resultant shock waves are 3 times the speed of sound, so Mach 3, as we call it. So they're supersonic, and that's about 300 kilometers per second. For coronal type gas, this is the gas sort of surrounds stars and surrounding galactic cores, which is typically at 1 million Kelvin. These shock waves are transonic, bit of a buzzword. It just means they're around Mach 1, so they're just around about 100 kilometers per second. So the hotter the gas, the slower the shock wave will move. And we also get gravitational interactions with near-miss collisions. So nothing has to actually collide, but you do get the effects of gravity on these near-miss, and that can supersonic shock waves as well. Right, enough of shock waves. Right, we're going to go back to the nursery a little bit on our radio astronomy. How are we on our radio astronomy? Right. So I'm sure people will recognize this as a stylized hydrogen atom with electrons in various energy orbits around. Don't worry if you don't. You don't need to know this for later, but I'm just going to go quickly through it. When we get an electron that moves from one orbit to another orbit, it either gives in energy, takes in energy, or gives out energy, depending on whether it's getting closer to the nucleus or not. And when it makes this transition between orbits, it gives off some energy or a photon at a certain wavelength. And we get various series. We get, don't worry about it, but they're called the Lyman series, the Balmer series, and the Paschen series. And from this, we are spectroscopic emission lines or absorption lines, depending on which way they're going. And we can see that the Balmer series is roughly in the visible light range. The Paschen series is in the infrared range, and the Lyman series is in ultraviolet. So this is how we get light given off. But being a more of a radio astronomer, I'm more interested in radio emissions. So that's what I'm going to be concentrating on. So various types of radio emissions. There's the thermal emissions, which are what we call the black body radiation. Now, everything in the universe gives off black body radiation. We do. We give off mainly infrared, so that's why we see that now. We don't give off much radio, hardly any, and we don't give off much visible light, but we do, as I said, give off infrared. Whereas stars tend to give off a lot in visible and infrared as well. So everything gives off thermal radiation. We're not worried about that. Then we look at what we call line radiation, line emissions. For example, the famous 21 centimeter hydrogen line, which I'll talk a bit more in a minute. And then there's the more continuum non-thermal type emissions, like cyclotron and synchrotron radiation. Not going to worry too much about it. Let's talk about cyclotron radiation. All we need to know is that it's caused by an electron moving in a circle in a magnetic field. When it does that, it will give off radio frequency energy. Typically, we see cyclotron radiation gives off something like 28 hertz. So quite a low radio wavelength. More interestingly, synchrotron radiation. This is when we get electrons moving at near light speeds, or termed as relativistic. And this, again, through magnetic fields. And this will give us frequencies of 10 to the 7 to 10 to the 11 hertz. So very high frequencies, so microwaves bordering on infrared. And how do we know what we're seeing? Well, we get a straight line spectrum for synchrotron, and we get a nice, that's our black body radiation. Anyway, just one more thing in this teach-in for radio, and then we'll get back to the galaxy collisions, honest. This is how the 21 centimeter line emission is caused. Once in every 100,000 years to a million years, a hydrogen atom, the electron, will decide to reverse its spin. It will undergo what we call a spin flip. So instead of being up, it will spin down. And when it changes, it will emit a nice photon of a wavelength of 21 centimeters, which is 1,420 megahertz. And that happens, as I said, once every 100,000 years to a million years. That's the half-life. So why do we see so much of it? Because there's so much hydrogen out there. So this is our main way of spotting hydrogen. So we look at the 21 centimeter. Now, another technique that we can use for spotting things, and that's masers. Now, I heard of masers, didn't know what they were, but then the MESA stands for microwave amplification by stimulated emission of radiation. So they're like lasers, only instead of light, we're looking at microwave frequencies. So here we have a very scary looking diagram. Don't worry about it. It's not scary at all. So we have a photon coming in, which has an energy which is equivalent to those that, if you don't understand, don't worry about it. But it's equivalent to a Planck constant h multiplied by the frequency. So it's got an energy. That's all you need to know. It's got a certain energy. And if this photon happens to wend its way past an unsuspecting atom that's in an excited state, so it's got an electron that's in an excited state, if it was to hit this atom, it will cause the electron to go into the less excited state, or the ground state. And what happens then, it will give off an amount of energy equal to the original photon. Now, this will only happen if that energy is the same. So the difference in energy is the equivalent to the initial photon. So in this way, we start off with one photon, and just by hitting another atom, we suddenly have two photons. So we've amplified it. And if this keeps happening, we get a cascade effect. And so we get a really bright, coherent, almost laser-like, hence the term maser, light coming from these sources. Now, I'll explain a little bit later how we can use masers to investigate resultants of galaxy collisions. So, when we're looking at masers, we can tell we're seeing a maser because we can define the equivalent blackbody temperature, which is called the brightness temperature, of the source. And if we work it out, we find out that if it was a natural phenomenon, then it would be a really, really hot, sort of 10 to the 10 Kelvin. And that's far in excess of any feasible actual temperature that we know of. So we know when we see this, we're seeing a maser. And these were first seen extraterrestrially in the mid-1960s. And it was seen by a hydroxyl, an OH molecule, 0.665 gigahertz, so well up in the microwaves. And because we're seeing so many of them now at different brightnesses and luminosities, we've had to come up with some other terms. So we now have killer masers and mega masers. It was like that, mega masers. And they come from these mega masers tend to come from the hydroxyl and water thought to be falling into in the accretion disk of massive black holes at the center of active galactic nuclei. And we can tell from studying this various characteristics about what's happening there, particularly in the form of star formation. So just a quick summary of what we can use various controls for. So we can use these maser lines for studying at frequencies of 1.4, 1.7 gigahertz, so microwaves. Basically, we can use microwaves, and we can use quasar synchrotron emission for studying quasars, and of more interest, we can use 1.3 millimeter studies, and this has just been done by the Event Horizon Telescope last year. You may remember that wonderful black hole image, or the event horizon of a black hole, sorry, the accretion disk of a black hole, I should say, that was seen last year. So we've got a picture of that in a minute. And also, we were talking about phosphine earlier. Phosphine is around 1.1 millimeters. So again, ALMA is a superb course for studying things like phosphine in Venus and black hole accretion disks like this. So getting back to galaxies colliding. So quick recap. So it takes 100 million years for an interaction to take place. It depends on the relative size of the galaxies, the temperature of the gas clouds inside, and the amount of gas interacting, whether it's wet or dry merger. So we can define a minor merger where a larger galaxy absorbs the smaller galaxy, it eats it, or a major interaction between similar sized galaxies, again going back to the Milky Way and Andromeda, where at first the identity will be retained, but as repeated interactions take place, there will be a merger into something less identifiable as the original. So we get major disruption caused by the gravitational mixing. And when we get this mixing, we get massive star formation triggered if it's a wet merger. And more interestingly, we get the merger of the central black holes at the center of the galaxy. And we've all seen the LIGO, for example, the gravitational wave detectors that have detected several of these black hole mergers. Now, the black hole mergers we've detected so far have not been big enough to be galaxy mergers. They've been relatively small, you know, sort of something like 60 solar masses. Now we're talking about supermassive black holes at the center of galaxies. We're talking millions of solar masses. So we haven't actually detected any yet, but we're still looking out. Merger scenario. Let's talk through what will happen to Andromeda and the Milky Way. Both similar sized galaxies, both blue type, gas rich. So it'll be a wet merger, and we are approaching one another at 110 kilometers per second on a direct collision course. So we saw the simulation at the start. The first pass will result in disrupted spiral structure and tidal tails. Now we can see examples of tidal tails actually happening, such as the antenna galaxy. So this is NGC 403839. See, you can imagine we've had the first pass through, and we've stripped out a spiral arm from one from each galaxy in terms of these tails. Happens. Well, a gravitational attraction takes over. So once, as I said before, once gravity takes hold, it won't let go. So there'll be multiple interactions. Momentum will pass the galaxies through each other, and then they'll get pulled back, and so on, until eventually they'll result in a stable state. And as I said before, the massive black holes will merge to form an even more massive black hole, and possibly a quasar. As the core material accretes towards the black hole, other material gets catapulted away. And both the attraction of material towards the center of the galaxy causes star formation, but also you get star formation in the material that's catapulted away. Either way, they get compressed, and that triggers the star. Example of the Cartwheel galaxy, which has got a lot of star formation going on in the middle, but it's also got star formation on the leading edge of the expansion. As you can imagine, that's expanding outwards. So the gas has been stripped from the inside of the galaxies and sent packing in every which direction. You can see there, as they causing star formation around the leading edge. Examples of that sort of thing. We also get, this is an example of the crushing of galaxy towards the core of the merger. And this is a starburst galaxy, M82. We see the expansion there of major starburst region going on in the center there. Right, now I'd like to talk about the Schmidt-Kennicutt star formation law. Saying is that the star formation rate is proportional to the amount of gas available, which blindingly obvious if you think about it. But there it is, proven with various examples all lying on that particular line. So we have this thing called the Maddow plot. Now, what it's doing, it's looking at star formation rates at various redshifts, so various distances away, i.e. various times in the past. And we can see that there's a definite peak of star formation at 10 billion years ago. So 10 billion light years away. We see that's when maximum rate of star formation. And it has since died down quite considerably, as we can see from the plot there. Don't know why that was the case. That is the case. Now, this is an image of the earliest known collision, so almost around the, just a little while after the Big Bang, so 13 billion light years away. So it's lovely name, B146566. So we've got a composite image here of dust, oxygen, and carbon observed by ALMA, again in millimeter wave bands, and then stars visible added to from the Hubble Space Telescope. So we've got an artist's of what that really looks like. So obviously, it's so far away to get a decent image, but that's an artist's impression. So this would have been one of the earliest galaxy collisions. So from this, we can tell galaxies have been colliding for the last 13 billion years. So what happens at the center of the newly collided and newly formed galaxy? Well, we have what we call an active galaxy nucleus, now an AGN. Now, this person that I'm not going to pronounce her name, it's Finnish, but you can see it written there. She described that AGN's, active galactic nuclei, can be split into this set of classifications and subcategories: radio quiet, radio loud, and starburst. And within that, we get Seyfert galaxies, and then in the radio loud, we get radio galaxies, quasars, and blazars. Now, it was thought that each of these types of galaxy, or AGN, were separate and with a different morphology, a different origin. But now it's believed that they're all just different views of the same thing. Galactic nuclei standard model. So let's just describe the diagram first of all. We've got the black hole in the middle, supermassive black hole. The black hole has its polar jets streaming out, so north and south, if you like. And then around the black hole equator, you get its accretion disk of material it's capturing, and that's slowly being pulled in to feed the black hole. And then surrounding this accretion disk, we get the dusty torus, as it's called, this area of dust and material created as a result of the accretion disk. So if we were to look straight down, if we just happen to be in line with the polar jet streams coming out from the black hole, then we think that this is a blazar. We would term this a blazar because there is so much radio frequency radiation being seen that we categorize this as a blazar. Now, if we were to see it from the side through the dusty ring around the black hole, we wouldn't see much visually, but again, and we would see a little bit of radio, mostly radio coming through, because radio is not obscured by dust. Only the visible light is obscured by dust. And then if we see from somewhere in between, we would see various types and categories of quasar and broadline radio galaxies. So as you can see, just from the viewpoint, you see different things. So instead of having totally different types of galaxy and black hole modeling, we've got just the one type with the one model, but we're just looking at it from different viewpoints. I think that's quite a nice, neat way of combining everything together into one description, one reasoning. So just to summarize that, so if we looking down the relativistic jet, we'll see some infrared, but mostly radio and very high level radio, primarily synchrotron. If we're looking at the hot innermost accretion disk, we'll tend to see ultraviolet and X-rays primarily. If we're looking at the outer accretion disk, we'll see it invisible, and so on. So as say infrared, we'll see from the hot torus around it, and as I said before, the dust torus will absorb the high energy electromagnetic rays of anything from light and ultraviolet upwards, but it'd be transparent to infrared and radio, so we can study it using that. So what do we get as a result of a galaxy collision? Well, one thing is quasars. Now, these are incredibly compact and luminous. They typically outshine the parent galaxy. They require a very large mass in a very small volume to work, to do what they do. And that will in turn imply that there is a black hole at their source as a power source. And another type is a Seyfert galaxy. These are like quasars, but these are actually associated with bright optical spiral galaxies, which quasars tend not to be. Remember looking down the barrel of the jet, if you like, coming from the black hole. So these are active radio galaxies, very radio loud, and typical examples would be L Lacertae objects and optically violent variable quasars. I've got OVV quasars. And starburst galaxies, galaxies that exhibit star formation about 1,000 times higher than we'd expect to see in a normal, whatever that means, a normal galaxy. So here's an example of a Seyfert galaxy. We've got a composite image again. We've got radio and visible. Radio is the more sort of blurry, bluey, purpley part, and the more standard visible image, the reds and the whites there. So you can see the radio parts of a galaxy are not necessarily in the same areas as the visible parts, the main star formation. Another one, ULIRG, ultra luminous infrared galaxies. Now, here's one. It's an extreme starburst galaxy. But if you look at it in visible, so that's on the left-hand side, this is the Hubble Space Telescope image. It's just a sort of an amorphous blob. But if again we look at it in using ALMA in radio, in millimeter microwave, we can see it's a massively more extensive object where things are happening. So here's another couple of examples. We've got Cygnus A and Centaurus A, two radio objects covered from within our own Milky Way. So both objects have roughly equal energy output, but one is small and bright, compact and bright, Cygnus A, and Centaurus A is less luminous, but a lot larger. Pays money, takes a choice, but the commonality is that the energy source behind it is roughly the same. So it just depends on how far the jets were blown when it was formed. So now coming on to, we've talked about star formation. Now there's another thing. quenching of star formation. This is stopping star formation. Now, there are two ways that galaxy collisions will cause an end to star formation. One is called the quasar mode, or the radiative mode. This tends to affect high luminous galaxies, high luminosity galaxies, which are young and fairly far away, fairly high redshift. Now these, we have this thing called the Eddington limit. I'm putting a lot of buzzwords in here. Perhaps I shouldn't, but sorry about that. But the Eddington limit is when the gas pressure equals gravity pressure. If you imagine the sun is in a nice equilibrium position with the gas pressure pushing out and gravity pulling in, and it's a nice equilibrium, as I said, and that is the Eddington limit. So what we've got here is when we're approaching this limit from one side, so the gas pressure actually overcomes gravity because of the compression, and we tend to get interstellar winds. So all the material between the stars gets blown out and it forms jets of gas. And this is something else we see in mergers. We see jets of gas coming out as a result. And one of the best example is a thing called Minkowski's object, which I'll show you a picture of in a minute. And the other mode is the radio mode or kinetic mode. This is for low luminosity but massive galaxies close by at low redshift. And again, we see high-speed gas jets with corresponding synchrotron radiation. So here's this object blown out from the side there. And so this is a jet of gas that's been expelled through a merger. And we can see that star formation ceased where the gas blew from, but where it's ended up, star formation has started again. Another strange thing, we've seen quasars disappear. Well, we've known for a long time that quasars exhibit variable luminosity. They are, in fact, they are very, very variable in terms of course. But this lady Lamassa discovered one particular quasar that had a really large reduction in its luminosity, the largest yet detected. And of course, following this, several groups got onto the bandwagon, and eventually some other 12 quasars were also found to be disappearing or growing much less luminous. So the issue here wasn't so much that they were diminishing, but it was the speed and time scale diminishing. So were these quasars shutting down permanently, or were they just sort of doing what Betelgeuse just did and faded away and then came back again? So as I said, all quasars will eventually grow quiescent when their black hole runs out of fuel. But these, as I said, were happening over such very short timescales of around 10 years. So that was the puzzling. So various suggestions came forth. One stated that the extreme variability was a fact that a very bright star was being eaten by the accretion disk and the black hole, which caused a bright flare, which then made us think that it was a quasar, but it wasn't really a quasar, it was just an ordinary black hole. And another was that the variation is just a result of a dust cloud obscuration. So again, a similar excuse as to what we think happened to Betelgeuse. A cloud got in the way, and but that really doesn't hold true because it wouldn't explain the radio variability as well. Because don't forget, cloud doesn't have any effect on radio; it just obscures visible and infrared. So the consensus is that it really was just a normal variation in the inflow in the accretion disk as it slowly runs out of fuel. So that one's really been put to bed. Not very satisfactory, but anyway. Right, there's other artifacts as a result of collisions that we can use. One of these is, may have remember a thing called Hannes Vorwerp. Now there's an extinct quasar 7, which had a former active nucleus, and we thought it was been quenched some 45,000 to 70,000 years ago. So that's the history. Now, along came Hanny van Arkel, a Dutch school teacher, who was taking part in the Galaxies zoo classification of galaxies, which I'm sure we've all taken part over the last few years. I know I've done a few. Never saw anything interesting though. Unlike Hanny, who had the first one named after her. Hannes Vorwerp. Well, Chris Lintott, who was running the Galaxy Zoo show at the time, he went on to conduct various observations and decided that this thing, whatever it was brightest in the visible G-band, so it's in the green. So it's a green, and was initially thought that it was being seen as an emission from caused by ionization from the nearby galaxy. But we now think, or Chris Lintott and et al. Suggests that it's actually an ionization echo of the light from the former active galactic nuclei, which was at the heart of the IC 2497 before it died. So it's a sort of a reheat. The length of time it took for the radiation to get from the center, from the source, to the Vorwerp, which is about 45,000 years or so, light years away. And so there was that delay. And so we're now seeing that. We're now looking back in history, if you like, hard to explain. So we're looking back in history because of that delay it took to go from the original source to the Vorwerp, then to be reionized and then emitted towards us. So that distance built in a delay. So it's a tool, or Chris thinks that it's a tool that can be used to study these active galactic nuclei, even though they've recently gone extinct. And luckily, this is not a unique phenomenon. Yeah, so as I've just said, that we can use this as a probe to study any of these quasars that close down the line. Picture of Hannes Vorwerp with its adjacent galaxy, with the dead quasar in the middle of it. Then there's other Vorwerp type objects that we've been discovered that we've been able to use as this historic probe, if you like. Now, I spent a lot of time boring you to death over mesas earlier. Now, mesas may be used quite a lot in studying things like magnetic fields, and we can measure distances with them because of the coherent nature of the light coming from these mesas. And we can also use it to study the masses of these massive black holes. So they're quite, and they can also be used to look at the central parsec or so, the 2 or 3 light years of an active galactic nuclei around the black hole, around the accretion disk area. Because they're coherent, the high coherence of the beams, the laser-like nature of the beams, means that they can be detected through these dense cloud toruses surrounding the accretion disk. So if we're looking at the AGN edge-on, if we can detect mesa energy coming from in there, we can tell a lot about what's going on in there. So we've got Vorwerps as one technique. We've got mesas as another. And another tool, another thing we can use the MESAs for is to trace sites of star formation, which again is an important thing to be able to do, as I said, because we can, if we can track where star formation is happening, we can track where these gas flows are being forced as a result of the collisions. So it all goes back to the collision, if you like, and this is a way of tracing it. Right. So by way of a sort of a summary slide now, we can use various types of observation. We can use our continuum observations to look at active galactic nuclei in terms of imaging, and we can classify merged types by looking, so we can tell if they're red type or blue type, wet and dry mergers, and so on and so on. We can look at the size of active galactic nuclei themselves, the size of the accretion disks, and so on. And then by looking at specific spectral line observations, like the hydrogen 21 centimeter line and MESAs, we can do a lot of analysis of star formation rates. We can look at the, we can investigate the environments that this star formation is taking place in. As I said, what's it like after the collision? We can look at velocities of the various components of the collision. And more importantly, we can actually get a reasonable distance my mind's gone blank for the word. Estimate, that'll do. Distance estimate of the AGN using either a MESA or the hydrogen line. And then we can use things like the Furverps to look at recently reflected and absorbed and emitted light. So we can look at historic behavior of the now quiet AGNs. So that's a summary of what we've talked about. And now just to finish off, we'll have another look at this video, and this time I'll point out the things that I've been talking about. So there we are, heading towards each other at 112 kilometers per second. And first contact is a glancing blow, but it's quite a devastating blow, so it's a major impact. And then you see they've got two tails coming out, like the Galaxies. As we see, there's a lot of material being ejected by that first contact. And so we're on for our second collision. Now, a lot of jet streaming of gas going on. A lot of quenching going on in the middle of the galaxies, but now we can see some star formation going on in the outer stretches of those little wisps of gas. You see they're getting quite bright. That's star formation going on. Bearing in mind this is taking place over, well, over the best part of half a billion years. A lot of the material thrown right out is now being attracted back in by gravity to reform. A significant amount of material is lost. A lot of it will get attracted back. So there we are. And I think that's it. And sorry if I got too technical there for you. I did get carried away a bit, but there we go.
I'm just unmuting everybody. Oh, it's not working.
Are we on video?
Can't hear.
Excellent. What a fascinating talk, Paul. And I mean, it looks like you really took to your dissertation at a deep level. So thanks very much for that wonderful talk, and lots of technical details in there. So I'm glad we've recorded it, so we can sort of go over it again, as necessary. But no, absolutely brilliant. And we've had a whole bunch of questions coming in. So I hope you can answer a few of them. And if it gets too many and you need to dash, because I know we need to sort of allow a little bit of time for some time. But let's give it a go, shall we?
Yeah.
Right. First question: is it inevitable? You mentioned about Andromeda and Milky Way merging, that perhaps our local group of galaxies, I think there's about 50 of them or so in the local group, will eventually all merge.
Chances are, given enough time. As I say, gravity is the weakest of the forces, but it's the most inevitable of the forces. It never gives up. So it was thought that Andromeda was going to miss us, until someone actually did the grunt work and worked the maths out, and it did. The component in our direction is 112 kilometers per second, so it is coming straight for us. But yes, I think for memory, I think the Magellanic Clouds, for example, will probably get swallowed up in the main crash. So I think it'll be a multiple crash anyway. But I don't think they bothered putting those in on the simulation model. Just saying.
And there was an associated question that came in later on, which said, if we were still on the Earth at that time, gazing up at this sort of collision or merger, what might it look like?
It's so slow. We wouldn't notice anything. The individual over a period of millions of years, you'd notice things changing. I mean, the star density would increase as obviously we merged in. The density of stars would increase, so that's what we'd notice. But quite honestly, there wouldn't be a lot of anything happening really.
Okay. Who came up with the terms wet and dry that you mentioned at the start?
That was. No, I'm not going to remember their names. I can. If you look back on the recording, at the bottom of the slide, I did have the names of the lead authors of the papers. Sorry, I can't remember them offhand.
Right. No.
A year, 18 months ago, I could recite them all, having typed it all up umpteen times. But memory dims, I'm afraid, for that sort of detail.
Okay. Well, we can look back on that one.
Yeah.
We normally associate an atom absorbing energy as resulting in electrons going to higher energy levels. Why, when you show that diagram of the maser energy interactions, why does it go to a lower energy level in a maser?
The only explanation I could come up with, so I thought this as well. The energy level goes up if the photon is absorbed by the atom. Now the photon isn't absorbed by the atom; it's just sort of passes through it, if you like. Think of it that way, otherwise your brain explodes. So you're not actually the atom isn't actually gaining anything. All it's doing is being affected, and it's the effect of going from higher. Anything will go. It's unstable. Anything will go from higher to lower energy at the drop of a hat, or passing of a photon. So that will knock from high to low. So that's how I look at it.
And that question came from John, but I can see Andrew is waving his hand. So
Yeah,
this is out of the ordinary, Paul. We don't normally allow oral questions.
Drunks out the audience. Yeah, lasers work when you've got what they call a metastable state, and these atoms or these molecules are sitting up there in this state, having been excited a long time ago. Normally, your laser is pumped, and it all happens pretty quickly, but presumably there's something in this that makes the metastable state very long. So the spontaneous emission is lower priority, and so it's time for another photon to come and stimulate the emission. So with this state, which is an unusual state, but it might be more in microwave energies. I just don't know. We didn't do. Mind you, the first book I was recommended to read was by a chap called O.S. Heavens, and it was called Optical Masers. So, I'm going back a bit, actually.
Masers have been around. Masers have been around on the Earth. Hello.
Yep.
Yeah.
So my screen suddenly went black. Then
No,
I thought I'd lost you. No, Masers have been around on the Earth for decades and decades.
Yes.
Only we're starting to see them in the sky. Yeah. No, you just reminded me that yes, there are these areas that. You said pumped. Yes.
Yeah.
Exactly. They're pumped into that metastable state. This is all coming back to me now. Yes. So and the mechanism for that is as a result of being close to the black hole. But there are other mechanisms. But the mechanism I was talking about in the AGNs was as a result of the black hole.
All right.
Yeah.
Okay.
Thank you.
Thanks, Paul, and for your contribution, Andrew. Another question here from Tony. Realise that colliding galaxies' suns are too far apart that they won't likely collide. But what would be the result if, in fact, they did?
Boom.
So we have two solar masses.
Yes. Yeah. Well, they did. Yeah. They'd merge. I don't know. I know what happens when a black hole merges, or a galaxy merges, but individual stars, I guess that. I mean, if they're one bigger than the other, then one would eat the other, or if not, they'd just merge, wouldn't they? Yeah.
I suppose they're not solid, are they? They're gaseous or plasma states.
Exactly.
So.
Yes, they just merge. Yeah.
Okay. When collisions occur and are disruptive, presumably some mass will be orphaned. I think you mentioned this in the simulation, and end up roaming into intergalactic space. But some of it's going to be brought back again under the gravity. Yes.
It's, inevitably, some will be lost. Yeah.
I just wondered if there's any evidence of that, and that I know we sometimes talk about stars wandering and Barnard star and so on, and whether there's any evidence of that. But, okay.
Not that I know of. Now, I would have thought that anything of a stellar mass would have enough gravity to be pulled back into the fold, unless it was really far out. I think it's mainly gas that would escape, and of course, with no way of really detecting it. Yeah. Once it gets so far away.
Okay. If wet gas-rich collisions produce more stars and globular clusters, which are usually found as older stars.
Yeah.
Does this help in renewing stars in older galaxies? And if globular clusters are usually found in older galaxies, does this indicate that the first galaxies were gas-rich?
Yes.
I can't even paraphrase that, I'm afraid.
So the globular clusters are normally found on the outskirts of the spirals, aren't they? remembering correctly on that. But yes, certainly. So, if you get an injection of gas, or if you get existing gas that's then crunched up, then you're going to get star formation. So yes, you do get regeneration after a merger. If it's a gas rich to a gas poor, then you're going to get a net donation of gas into the gas poor, and so star formation will start again. I'm not too sure on the mechanics of the globular star cluster formation, I'm afraid, but it would sort of make sense to me. Yeah, so yes.
Unless it was perhaps one of those little orphan packages that sort of then
Could be. That's could be.
were galaxies colliding? Oh, sorry. How were there already galaxies colliding so soon after the Big Bang? I think you referenced a colliding galaxy
indeed.
just about
Yes.
less than 1 billion years or so.
Yes, that was quite a surprise finding that one. So yeah, we now know because of that collisions have been happening all the way through. Well, obviously the universe was a bit smaller in those days. Whether that's got any statistical relevance or not, but yeah, well, obviously they were. My question that came from this particular image to my tutor was where. So if we tend to be found at the center of galaxies, and we know that they get bigger on collisions and mergers of galaxies. So working backwards, they were presumably smaller, but still massive. So where did the first supermassive black holes come from?
Yeah.
So which came first, the black hole or the galaxy? And no one could answer that one adequately. I mean, they all had their best guess, but yeah. So I'm still looking for the answer on that one.
Oh, perhaps that's a PhD. PhD.
Well, exactly. But the best thing I heard was that they were sort of spontaneously formed. So galaxies form. No, get it right. Stars formed first, then black holes and galaxies all sort of formed almost spontaneously, if you like. Yeah.
Okay.
I don't like that explanation, but that's the best they've got.
I think that's relating similarly to the next question as well. Were galaxies colliding more in the early part of the Big Bang before expansion, and not so later due to expansion?
Yeah.
Yeah. Okay. Spin direction. Yeah, we know sort of galaxies spin, and
Yes.
is spin direction formed by the black holes, and can this be affected by collisions?
Well, everything likes to spin. Angular momentum is a natural state of affairs. Can it be affected by collisions? Well, if there's given enough energy, you can if you swirl around, the old water going down the plug hole. If it goes the way, which is not dependent on whether in the north or south hemisphere, but you can make it go the opposite way just by swirling it in the opposite way. So if you put enough energy in like that, gravitational energy, then you can get the spin to change. But it's just a natural phenomenon. Spin happens. Angular momentum. In the beginning, there was angular momentum, and it has to be maintained. So spin is a natural thing. It's not. I don't think it's particularly driven by black holes. I mean, black holes, again, material falling into black holes, the accretion disk will develop a spin, obviously, so as it spins in. So it's just a natural state of affairs.
Okay. Last couple of questions. The massive events you describe must involve a lot of kinetic energy. Is this because several or many objects are involved, or is there some sort of focusing mechanism which brings many objects together at once? That's gravity, isn't it?
Yeah,
Anyway,
gravity. Yeah. Well, you work out the kinetic when you've got things in motion, you get kinetic energy, and so yeah, the sum, the mathematical analysis that was done was just assuming the masses of the Milky Way and Andromeda galaxies, roughly, and then was it half mv squared? You know, so we've got the mass, we know the velocity of the heading towards each other. So it's just simply done that way. So where does the energy come from, or where does it go? Well, it goes in, they say, gravitational energy, but also then in frictional, you get heat as the so on. So yeah, it's also anyway, that's going on. Yeah, gravity is the main energy source, and it's the simple sum.
excellent. And I think looking at the last two questions, we've already answered them, or you've already answered those, Paul. So I think that's all the questions, and I'm not going to open it up to the floor. We've already had one like that. So perhaps once again we can all thank Paul in the usual way for a fascinating talk and some excellent answers. Thanks very much, Paul. So I think I'm going to hand back to Les, who I think you're going to conduct the rest of the meeting. And Paul, thanks very much. If you can stay, you're welcome to stay for our AGM. I guess you may have something else to do.
Yeah, I've got the all well Zoom meeting to go to now. So I'll say cheerio and thanks once again.
Until next time.
Indeed.
Yeah.
Thank you very much, Paul.
Bye now.
Cheers. Bye-bye.